Okay, we're going to start talking about Chapter 2, Atoms, Molecules, and Ions. We haven't got to the chemistry yet. We're slowly building up to it. So to understand how chemistry works, you have to understand about the atom. And I can understand about the atom if I get this one. Okay. There we go. The atomic theory. We're going to talk about that. Just a general history of it. Started off with a man named Dalton. His theory was elements are composed of extremely small particles called atoms. All atoms of a given element are identical, having the same size, mass, and chemical properties. He said the atoms of one element are different from the atoms of all other elements. That's kind of true, but not really. We know that when we get to isotopes, we can have the same element with slightly different masses. But yes, all iron atoms are the same or similar, and different elements have different atoms. Compounds are atoms of more than one element combined. So in a given compound, you have the same types of atoms always present in the same relative numbers. So if you have water, you always have H2O. If you have H2O2, you don't have water, you have hydrogen peroxide. In a chemical reaction, what occurs, you rearrange the atoms. You don't create or destroy them. That's sort of what's called the conservation of mass. So really all chemistry is we have a bunch of compounds over here, on the left. We take them apart into the individual atoms, then we assemble them in a different arrangement on the right. That's chemistry pretty much in a nutshell. And to do that, it takes energy. We'll cover that later when we get into thermodynamics. A man named Proust had what's called the law of definite proportions. So here, he's taking a sample of carbon dioxide. Doesn't matter how much he takes, 123 grams, 50.5, 88.6. And if he breaks it down into the carbon and oxygen and gets the mass of each, he always gets the same ratio, 2.66 to 1. It doesn't matter how much you have of a compound, it's always going to be the same ratio. If he does carbon monoxide, we have a ratio of 1.33 to 1. No matter how much of carbon monoxide you take. And if you compare the two ratios, the ratio of oxygen and carbon dioxide to the ratio of oxygen and carbon monoxide, it's 2 to 1. CO2, you have 2 oxygens. CO, you have 1. So it's 2 to 1. Always comes out that way. So here in the sample problem, we have water and hydrogen peroxide. If you decompose water into oxygen and hydrogen, you get 0.125 grams of hydrogen for every gram of oxygen. Do the same thing with hydrogen peroxide, you get 0.063 grams of hydrogen for every gram of oxygen. So again, we're going to do the ratios. So 0.125 for the hydrogen to oxygen ratio in water, and 0.063 hydrogen to oxygen water. So it's 2 to 1 hydrogen to oxygen. So water is H2O. Hydrogen peroxide is H2O2, 1 to 1. 2 hydrogens for 2 oxygen. Okay, here they're doing sulfur and oxygen. I'm going to kind of skim over this one. SO2 and SO3. Same principle, you're going to you decompose them, take the ratios, and compare the ratios. So when you do it, it comes out 3 to 2. That's what you expect, SO3, SO2. 3 oxygens, 2 oxygens. 3 to 2. Questions about that? It's something you don't really need to worry about, but that's part of the history. So here we're going to look at the discovery of different subatomic particles in an atom. We're looking at how they discovered the electron. So they use this thing called a cathode ray tube. And they pass a beam of electrons, that's what's generated between the cathode and the anode, past the magnet. And sure enough, it was deflected. This is an evacuated tube. How many folks seen a cathode ray tube? No? Okay. If I take this wide end here, and I coat this glass with something that phosphoresces.
Not like a light bulb?
Not like a light bulb. So when the electrons hit it, it lights up where the electrons hit. And I scan the electrons back and forth and up and down real fast. Yeah, I know you've all seen it. It's a television. It's the picture tube in a television. Okay, what they do in a television screen is they scan that beam left to right and then top to bottom real fast. It's called rastering. And those things light up, and depending on what the phosphorus is on there, you either get black and white or color. Okay. Computers, before the flat screen monitors, what kind of monitors did we have? Remember those big bulky things? What were they called? You remember? CRT monitors? Guess what CRT stands for? Cathode ray tube. So that's what you had in there. And you know, it's an evacuated tube, which is why if you ever broke a picture tube on TV, you got this big kaboom because you released that vacuum. So there's another example of a cathode ray tube. And you can see it passes a magnet over it, the ray is bent. So that means those particles must be charged. Since they're repelled by the negative end, the particles must be negative. That's how they came up with the electron. Another experiment they could do is the Millikan oil drop experiment. In this apparatus, you can get a fine mist of oil droplets. You can put a charge on them and put them between charged plates. You can actually float the oil droplets. So that's another way they saw what an electron was. Now, J.J. Thomson calculated the charge to mass, it should say ratio, not ration, of the electron at 1.76 times 10 to the 8 coulombs per gram. And a coulomb is 1 ampere second. That's what the A stands for. The charge of the electron is negative 1.6022 times 10 to the minus 19 coulomb. So the mass of the electron, taking the charge and divided by the charge per mass, mass of the electron is 9.10 times 10 to the minus 28 grams. Very small. So much for the electron. This slide, I'm not exactly sure why it's in here, but this shows a radioactive substance going through some electrically charged plates, and we can separate, should be alpha particles, beta particles, and gamma rays. And later on, we will actually go to 152, talk about nuclear chemistry. So Rutherford, at that time, scientists thought an atom was pretty much solid ball, or a ball consisting of protons and electrons, just evenly all mixed up in there. An atom has no charge, so you got to have an equal number of positives and negatives. So if you have a bunch of atoms next to each other, let's say gold foil. Gold foil is what state of matter? Solid. So I'm going to bombard that with alpha particles. Alpha particles are real small. So and they're solid, they have mass. So if I throw a particle against the solid, what happens? Bounces off. Wow. Right? So he did this experiment. He put gold foil, and he put a zinc sulfide screen, which is like a photographic plate. It lights up when it gets hit. Zinc sulfide is a phosphor. And he shined alpha particles at the gold foil. And guess what? Most of them didn't bounce back. Most of them went right through. The gold foil's a solid. Well, that led to the theory that atoms aren't solid. We have a small nucleus this way, and a large area of electrons around it. The nucleus contains the protons and the neutrons, and the electrons are outside, and a cloud around it. So the nucleus, he proposed, the nucleus, very dense core. And the positively charged particles are called protons. Well, this other guy, Chadwick, bombarded a thin sheet of beryllium with, just say, alpha particles, and he got a very high energy radiation emitted. Now this radiation wasn't deflected by either a magnet or electronic field. So that's how they discovered the neutron. They have a mass just slightly greater than that of a proton, really negligible. So there's the example of an atom. So you see right in the middle there, that little red dot, that's the nucleus, which consists of protons and neutrons. Everything around that sort of grayish ball there, that's where the electrons are. So to get a kind of concept of that, if you think of a football stadium, if you think of the electrons going around the outer seats, the nucleus would be the size of a grape in the middle of the 50-yard line. That's where all the mass is. So there's a comparison of all the particles. The electron, see its mass, its charge. The charge unit is -1, proton is +1, the neutron is 0. Notice the proton and neutron have about the same mass, which is a lot greater than the electron. So when we get down to calculating atomic masses, we don't really include, even though the electrons have mass, we don't include them in the calculations because they're negligible. It's like going into the grocery store and saying, I'm going to buy watermelons, and for some reason they're selling it by the pound. So you get 5 watermelons, and you go over to the scale, and you throw on 5 watermelons. You see the scale. Then you say, well, I'm here, I might as well get 12 raisins. You take 12 raisins and throw them on there. That needle on the scale is not going to move. As compared to the watermelons, you're not really adding anything with the raisins. So you can think of the raisins like the electrons, and the watermelons as the neutrons and the protons. So remember, protons are positive, P positive, neutrons are neutral, N for neutral. Okay? Or you could say, proton walks into a bar, asks the bartender for a drink, says, "Are you sure?" He says, "Yeah, it's positive." Neutron has a drink at a bar, says to the bartender, how much do I owe you? Bartender says, for you, no charge. Okay. And since I'm recording that, it's going to live on forever. Atomic number, the symbol is Z. It's the number of protons in the nucleus of each atom of an element. So, each element has a unique number of protons. Hydrogen has 1, helium has 2, carbon has 6, fluorine has 17. The number of protons tells you what element it is. If you change the number of protons, you change the element. If you have 6 protons, you have carbon. If you do something, you change it to 7, you no longer have carbon, you have nitrogen. And if you go on to 152 nuclear chemistry, you'll see how you can change those. The mass number is the total number of neutrons and protons present in the nucleus of an element. So the mass number is the number of protons and the number of neutrons. So atoms said, what charge does an atom have overall? It's neutral. Yeah, the atom's just a line there, not electrostatic attraction. So they're neutral. So if Z, the atomic number, is the number of protons, how many I forgot the number of electrons?
The atomic number from mass.
Atomic number from mass will give you the number of neutrons. I want to know how many electrons. So carbon has 6 protons. How many positive charges does it have? 6. So remember I said atoms are neutral, so how many negative charges do I need to balance it out? 6. So how many electrons do I have to have? 6. I have 6 negative charges to match the 6 positive charges. So we said Z, the atomic number, is the number of protons. It's also the number of electrons, because it has to balance out. So if you look at your periodic table, you're going to see an elemental symbol. Depending on the one you have in your book has the atomic number on top. Those are the ones that are whole numbers and they go sequentially, 1, 2, 3, 4, all the way up to, I think right now, 119. The mass numbers, A, are the ones that in your book, in your periodic table, are underneath. You can tell because they're not whole numbers. Carbon is 12.01. Hydrogen is 1.008. The mass number will always, if you're confused, the mass number will always be higher than the atomic number because the mass number includes the protons plus the neutrons. So most elements have 2 or more what they call isotopes. So isotopes, we can't change the number of protons, but we can change the number of neutrons. So this first one here, hydrogen, is our everyday hydrogen, has atomic number 1, mass number 1. So how many protons does it have? How many electrons? How many neutrons? No. None. It's the mass number minus the protons. So 1 minus 1 is 0. If we go to deuterium, mass of 2, atomic number 1 again, because it's hydrogen. How many neutrons? 1. It has 1 neutron. How many protons? 1. The atomic number is the number of protons. How many electrons? 1. Final one, tritium, mass of 3, atomic number 1. How many protons? 1. Atomic number is always the number of protons. How many electrons? 1. How many neutrons? 2. 3 minus 1. Chlorine, 35. So 35 is the bigger number, so that's the mass. Atomic number 17. How many electrons?
17.
How many neutrons?
18.
18. How many electrons? Everybody got that? I can do pretty much anyone in the periodic table. So here we're doing uranium, 235, 238, different isotopes. So you see uranium 235 has 143 neutrons, 235 minus 92. And uranium 238 has 146. So remember Dalton said all atoms of the same element were identical? Well, he didn't know about isotopes. Most elements have multiple isotopes. So, okay, here we go. We did chlorine, and we did the other chlorine. Potassium 41, how many protons? That you need the periodic table for. You need to look it up. I think it's in the back of your book. It says, not knowing if you got, yeah, it's right where you know, right there. Go turn it all over. It's like third last page, second last page. If you have the loose leaf book. Is that the front?
You've been going for a while.
All right. All right, I made a mistake. It's at the front in this book. Okay. My other class is in the back. Okay, so if you look up potassium, how many protons? 19. Look up K in your book. All right, so if it's got 19 protons, how many neutrons does it have? 22. How many electrons? 19. Carbon 14, how many protons? 6, carbon 6. How many neutrons? 8, 14 minus 6. And how many electrons? 6. So you should be able to read any periodic table. So some of them, the numbers are inverted. Let's talk about the periodic table. Did chemistry in high school and your chemistry teacher made you memorize the periodic table? That was a waste of time, waste of energy, because you have one. So because of Wallen edition. The periodic table in the Wallen edition? Okay, all right. I got a bunch of them in my office. You have really good eyes to see those. Okay. The one in your book is color-coded, so it tells you a lot of things without having to memorize it, because it's like a map. You don't memorize maps usually. So if you look at the ones that are that light gray color, from aluminum all the way over, those are metals. If you look at the light blue ones, those are nonmetals. Notice hydrogen's over on the left. Should really be with the nonmetals, but they put it on the left because of its atomic structure. It's right in there. What about those yellow ones? Boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Those are the metalloids. Those are the ones that I'm not quite sure what they're going to identify with. So they're metal, non-metal. Properties of both. There, so right away, if I said copper, quick, metal or non-metal? There you go, look at the table for that. If you don't know copper's metal, okay. But if I said osmium, atomic number 76. Metal or non-metal? Metal. If I said selenium, 34. Non-metal. Okay. And of course, polonium, 84 is metalloid. So, there. Partway done. I'm going to do some other descriptions here. The rows that go across are called periods. The columns are called groups or families. Notice the numbering at the top, 1A, 2A, a whole bunch of B numbers, then 3A, 4A, 5A, 6A, 7A, and 8A. So all the A's, 1A to 2A on this side, 3 through 8, those are called the main group elements or the representative elements. We talk about a lot of the rules of the periodic table, those follow the rules. So to get from 2A to 3A, we have to make a transition. Oh, so all the elements in between the 3B to the 2B are called the transition elements. You don't quite follow all the rules perfectly. Then you go down here, lanthanum. Look, we go from 57, and that should actually be up with the barium, or 56 for barium. And what's the next one? 71 lutetium. What happened to the rest? They moved them down here from lanthanum to ytterbium. And from radium to lawrencium, it goes from 88 to 103. What happened to them? They're all moved down here from actinium to nobelium. So the top row, those are the inner transition elements. The top one are called the lanthanides, and the bottom one's called the actinides, lanthanum and actinium. They took them out for two reasons. One, it makes the table not as wide, so it fits on the paper real good. And later on, when we talk about electron configurations and that, you'll see why those are been pulled out. So elements in the same group tend to have similar physical and chemical properties. What do we mean by that? If we take NaCl, which is sodium chloride, salt, table salt. Sodium is in what column? First column. Under sodium is what? Potassium. You do that from memory? Okay. KCl is potassium chloride. Well, what do we use potassium chloride for? You buy it at the grocery store. No, it's not next to the mushrooms.
Bananas.
No. Well, bananas have potassium. But sodium chloride, if you buy sodium chloride in the store. All right. I have high blood pressure, borderline. So my doctor tells me to avoid, because salt has sodium. So I have to use a salt substitute. Guess what that is? Potassium chloride. So I wrote it up there. If you're not using one of the herb substitutes, potassium chloride can be used as a salt substitute. And it's also used in solution and injection if you want to stop somebody's heart really fast. Like lethal injection, or veterinarians use that sometimes if you put an animal down. It'll stop your heart in a heartbeat. Okay, for those of you who aren't familiar with metals, they're good conductors of heat and electricity. Non-metals usually aren't. A metalloid properties similar between both. So, some of the groups have common names. Group 1 are called the alkali metals. You think of sodium hydroxide, which is lye. If you think about lye solutions, and that sometimes referred to as alkaline. That's where that came from. Group 2, the alkaline earth metals. So you think of your alkaline, energizer, bunny. Group 6 starts with oxygen. That's the chalcogens. You don't hear that referred to too much. Group 7, fluorine, chlorine, bromine, and iodine are the halogens. And group 8A are the noble gases. When I was in high school, they were still calling them inert gases because they wouldn't react with anything, but they did find a way to make some of them react under extreme conditions. So now they're called noble gases, and that's really the key to the periodic table. And I think that's it. Is that a good stopping point? Okay. That is a good stopping point.